We found derivative rules for sine and cosine, but remember there are 4 other trig functions that we should probably find derivatives for: tangent, cotangent, secant, and cosecant. In applications, sine, cosine, and tangent tend to be the most important, so figuring out a derivative for tangent will definitely be important. But there are some important applications for the other 3 trig functions as well, so we'll find derivatives for them. The nice thing about these other trig functions is they're all built out of sine and cosine, right? They're all quotients of sine and cosine, so we can just rewrite each of these in terms of sine and cosine and then use the quotient rule. So let's see, tangent is sine x over cosine x. So now we can use the quotient rule. So let's see. It's derivative of the numerator, derivative of sine of x, times the denominator with no derivative, minus numerator times derivative of denominator, so derivative of cosine, all over cosine squared, right, denominator squared, so that's cosine squared. Now in the numerator, let's see, derivative of sine, that's cosine, times another cosine, so cosine squared, minus sine of x times derivative of cosine, but that's minus sine. This is all over cosine squared. Now in the numerator, well look, here's a minus and another minus, so these are pluses. And now we have sine times sine, so that's sine squared. So the numerator is cosine squared times sine squared. Well, that's 1, according to the Pythagorean identity. So 1 over cosine squared, but that's secant squared. So the derivative of tangent is secant squared. All right, let's try cotangent. Well, you can see that, cotangent is essentially the same as tangent, it's just it's upside down. So when we, the same sort of thing is going to happen. We're going to end up using the quotient rule, and we'll have to keep our eye out for opportunities to use the Pythagorean identity, but really the same sort of thing is going to be happening. So derivative with respect to x of cosine x times sine x with no derivative, minus cosine with no derivative times sine with a derivative, sine, there we go, okay, all over sine squared. So this is exactly the same, it's just the role of cosine and sine has switched. So derivative of cosine is minus sine x times another sine x, so sine squared x, minus, and then here's cosine x times its derivative of sine is another cosine, so cosine squared, all over sine squared. Now, negative sine squared x minus cosine squared x, this is just the negative of the Pythagorean identity, so you get minus 1 as a result. And the denominator is sine squared x. There should be an x here. And minus 1 over sine squared x, that's minus cosecant x. So, based on the fact that cotangent is the reciprocal of tangent, it's not a big surprise that we get a cosecant instead of a secant here. Oops, this should be squared. It's not a big surprise that we get cosecant squared instead of secant squared, but we actually also get a minus sign, which is a bit of a surprise. Okay, now let's try secant. Once again, we're just going to use the quotient rule because secant is just 1 over cosine. So derivative of the numerator times the denominator, cosine, minus the numerator times the derivative of the denominator, like this, all over denominator squared. Well, this first piece, the derivative of 1, that's 0. So this entire first term is gone. And then in the second term, we get minus 1 times the derivative of cosine, that's minus sine x. So these minuses cancel over cosine squared x. So we get sine over cosine squared. And it's hard to know exactly how to write that, but one nice way to write this is to split up the numerator, or to split up the denominator, because we have two factors of cosine. So split them up like this. There. So we'll have 1 over cosine x times sine x over cosine x. And this is secant x times tangent x. All right, so the derivative of secant is secant times tangent. All right, for cosecant, of course, it's going to work out mostly the same as for secant. 1 over sine x. So that's derivative with respect to x of 1 times sine x with no derivative minus 1 times derivative of sine x all over sine squared. Okay, again, this first term is gone because the derivative of 1 is 0. So we get minus 1 times derivative of sine x is cosine x over sine squared x. So as with secant, we get something very similar, except there's this minus sign. So let's put that minus sign out in front, and then we can write 1 over sine x times cosine x over sine x. And that's minus cosecant x times cotangent x. All right. So this is the derivative of cosecant, and this is the derivative of secant. You can see that the cofunctions are sort of the derivatives of the cofunctions are the derivatives of the originals, but also with the minus sign. So since to turn the derivative of secant into the derivative of cosecant, you take the derivative of secant and you put a co in front of each piece, right? Secant becomes cosecant, tangent becomes cotangent, and then you also stick a minus sign in front. That's also true for cotangent up here, right? To get the derivative of cotangent from the derivative of tangent, you stick a co in front and you put a minus sign in front as well. All right, now that we have derivatives for all of the trig functions, we can use them to find rates of change in any situation where a trig function shows up. So here's an example. Suppose we have a laser pointer shining at a wall that's 5 meters away, and the laser pointer rotates horizontally so that the point of light moves along the wall. So what I have in mind here is, here's a bird's eye view. We're looking down from above. Here's the wall, and then there's a laser pointer here, which maybe it's a red one. Okay, so it beams a spot of light onto the wall, and as this, if we rotate this laser pointer this way, that's going to make this point go along the wall that way until it rotates far enough, and then the point will actually reappear back here and move that way. All right, so if the wall is 5 meters away from the laser pointer, and initially it's pointing directly at the wall so that it's perpendicular, like this, and it's rotating at 1 radian per second. Let's find how fast is this point of light moving as a function of time. Well, I guess what we need to do is find the position of this as a function of time, because if we have its position, it's moving along a straight line, the surface of the wall. So if we have its position, we can just differentiate its position to find its velocity. So let's use this wall like a ruler. Let's call this position 0, and then position 1, and then position 2, and then back here is position -1 and position -2, and so on. So what we'll need to do for the position, let's write f. So f of t is going to be the position at time t. And so the velocity will be just the derivative of the position function. We just need to figure out what is this position function. All right, so I guess first let's figure out, after we waited t seconds, how far has this laser pointer rotated? So theta could be the angle that the laser has rotated after t seconds. But since this laser pointer is rotating at 1 radian per second, this is just going to be 1 radian per second times t seconds, right? Second units cancels, and you just get t radians. So after t seconds, this laser pointer has rotated, so then it's pointing up this way, and it's rotated this amount theta. And theta is really just t radians. All right, now the position is going to be, after the laser pointer has rotated to this position, the spot of laser light is going to be up here. So its position is going to be this distance. We need to figure out, what is that distance as a function of theta? Well, we know the bottom side of this triangle. This is a right triangle here. We know the bottom side. We want the right-hand side. Which trig function is it that relates the opposite side to the adjacent side? Well, it's tangent. So tangent of theta is the side we want, right? This side, that's f of t. So tangent theta is f of t over the adjacent side, which is 5. All my distances are in meters, so I won't write the meters for the time being. And then we can rearrange this to find our function f of t. So f of t is, we can just move the 5 to the other side. 5 tangent theta. But remember that theta was really just t radians. So this is 5 times tangent of t. All right, so finally we have our position function. Now we just need to differentiate it to find our velocity function. So our velocity function is the derivative with respect to t of our position function. So derivative with respect to t of 5 times tangent of t. We can move the 5 outside of our derivative because it's a constant multiple. So that's the constant multiple rule for derivatives. And now we just need the derivative of tangent. But that's one of the ones we worked out. The derivative of tangent is secant squared. All right. So why does this make sense? Well, if you imagine what the position of this point is going to look like, remember that when the laser pointer is pointed this direction, that's an angle of pi over 2, the laser actually isn't going to be hitting the wall at all. So at pi over 2, something funny is going to happen. And 5 tangent x, right, that's our position function, 5 tangent x looks like this. And if we go backwards in time, it goes like this, right? And this kind of makes sense because when the laser is almost parallel to the wall, this point is going to be moving very quickly, right? Imagine shining the laser out this way. If a small change in angle will make the point of light move a long way along the wall. So it makes sense that we have this vertical asymptote here. So what about the velocity function, 5 times secant squared t? Well, secant squared looks like, on this interval, secant squared looks like this, roughly speaking. So when the laser pointer is pointing directly at the wall, the velocity should be smaller. Looks like it's going to be 5 actually. And when the laser is almost parallel to the wall, the laser should be moving very quickly. But that is true. That makes sense. When the laser is directly at the wall, a small change in angle will produce only a small change in position, so the velocity is smaller. When the laser is almost parallel to the wall, a small change in angle will produce a big change in position, and that means that the velocity up here is much bigger. And the graph is showing that. So it's always nice when the graph matches what you think should be happening.